Hello class, today I'm going to solve one very interesting question which is going to include the material we learned previous weeks and this week. Let's see what is the question about. We have a 20 millimeter diameter sphere made of steel with these properties. It's dropped into the large tank of water. The sphere is initially isothermal at this temperature, so let's highlight this. So this is the initial temperature of the steel sphere and drops until the center temperature is 320 Kelvin. So the initial temperature is 360 and reaches to 320, and the water temperature is 280. So this is T infinity for the water. The sphere may assume to be quickly reach the terminal velocity in the water. Okay, you may ask, what is the terminal velocity? Terminal velocity is the constant velocity when we have a balance between buoyancy and drag force and weight. If there was a balance between those three forces, we are going to have terminal velocity. Okay, the question says find that terminal velocity as a first part. The second part says find the minimum height of the water tank which we need to cool down this steel from 360 to 320. Okay, so let's start with drawing a schematic figure to know what type of geometry we are dealing with. So we have a tank like this, and this is a water inside this tank. Okay, I make coloring blue. Okay, so the temperature of the water is 280 Kelvin. We have a ball, a sphere here. Originally it is 360 Kelvin, and when we drop it after some time and some height, it is going to reach to 320. So it is going to lose temperature when we drop it here. So because we are going to find terminal velocity, and it is can happen that terminal velocity when we have a force balance, we need to draw the free body diagram. Free body diagram of that ball. So let's draw that sphere, and this is going to be my weight. So W, we are going to have buoyancy force, we call it FB, and we are going to have a drag force which is going to be FD. So let's put the equations for each of these forces. So for the drag force, we are going to have the drag coefficient multiplied by the projected area times half rho v square. So you may say, what is this projected area? Projected area is the area when you watch perpendicular to this surface we can see. So it's going to be a circle, and rho, which rho? It is going to be for fluid rho. So I'm writing red to make sure you understand. So the next one is going to be weight, which is really easy, mg, but we don't have mass, so we convert and use it, use density. So density times volume times g. So this time, because this is the mass of the sphere, it is going to be for solid. And the last one is buoyancy force. Again, from ME 2512, you know that buoyancy force is rho Vg, and this rho is going to be for fluid. And so let's write down the projected area is pi r square, and the volume is for sphere is 4 divided by 3 pi r cube. Okay, now we have all the information we need to to keep the balance and have a terminal velocity. So let's write the summation of all those forces must be equal 0. So I'm going to keep this the drag force one side, the other to the other side. So rho for solid volume minus rho for fluid times volume times g must be equal the drag coefficient projected area half rho velocity square. I'm going to call this velocity because we are looking for terminal velocity. I'm going to call it u infinity, which is terminal velocity. And if we rearrange everything, we are going to have volume to projected area, drag coefficient, rho s, rho f minus 1, g. Okay, so let's see. The volume divided by AP, I have the values here. It is going to be 4 divided by 3 r. So I can plug those numbers inside. So let's do all the calculations. So if you put the value of r, which is half of this diameter, so it is going to be 10 millimeter. And we know the value for g. We know the density of the solid, it's given. Density of the fluid, you need to find density of fluid at T infinity. So T infinity is 280. And yeah, the rest is done. So if you put all the number, the final is going to be 1.793 divided by drag coefficient. Okay. So if I want to find this terminal velocity, I need to know what is the drag coefficient. Let's go and check our lecture notes. For week 5, the second lecture note, page 18, we have this graph. Let me zoom it. As you can see, this is the lower one is for sphere. If you want to find drag coefficient, you need to know Reynolds number. Okay, let's find Reynolds number. So let me write Reynolds number formula. It is going to be velocity times diameter of the sphere divided by viscosity. Okay, here I have velocity, but I'm looking for the velocity, so I can't find Reynolds number because yeah, velocity is not given. So what I'm going to do, I'm going to iterate. So let's draw a table. Reynolds number, drag coefficient, and terminal velocity. Okay, let's see what number we can start. We can start with any number we want. Definitely not smaller than 0.1, not bigger than 10 power 6. So we can select any number, but I'm going to select the easiest one because I want to have an easy calculation. So CD here 1 shows us it's around 100. So if Reynolds number is 100, CD is going to be 1. So it's a good starting point. So we are going to select Reynolds number 100 and CD is going to be 1. If I do plug these numbers, this CD inside this, the U infinity is going to be 1.3 meter per second. Done. Okay, this is the first one. Now I have the velocity and I'm going to go back and calculate Reynolds number. Okay, so I have the velocity, I can calculate Reynolds number, but I need to find this nu. So because you know nu is mu divided by rho, so nu must be found at what temperature? At film temperature, because because temperature is going to be changed, and we have different temperatures. Remember, we talked what is the film temperature. Film temperature is the average temperature between surface temperature and T infinity. Okay, let's go back to the question. Here we have two surface temperatures, the initial one and the last one. So the easiest way is going to be just finding the average of these two. So I'm going to do that. So to find the surface temperature, I'm finding the average temperature of those surface temperatures, 320, which is going to be 340 degree, and then plug that number to get a film temperature, which is going to be 340, T infinity is 280 divided by 2, it is going to be 310 degree. So nu, I'm going to find nu for this T infinity, which is around 1.42 times 10 power minus 6 meters square per second. Anyway, so you find this T U infinity, you put inside Reynolds number and calculate Reynolds number. If I put this number, this time the Reynolds number is going to 37,600, much bigger Reynolds number. Now I need to go back to the graph and see, okay, it's almost 40,000, so 10 power 4, 10 power 4, this is 20, this is 40, it's about here, so it is going to be almost 0.4. So with this Reynolds number, drag coefficient is going to be 0.4. Now I found drag coefficient. Using this formula, I can get the velocity. So if you do the calculation for velocity, it's going to be 2.11 meter per second. Again, I'm going to repeat this. Put this velocity inside Reynolds number formula. If I do that, this time it's going to be 60,000. So for 60,000, it's here. It's again almost 0.4 or 0.5. I'm going to say 0.41, for example. And if you do the calculation for U infinity, it's going to be 2.09. Okay, now you can see when we're changing the Reynolds number, the U gradually reaches the number we want, and it doesn't change that much. So CD is going to be around 0.4, and actually we are looking for U infinity, so I'm going to consider U infinity almost 2.1 meter per second. It's a good approximation. Okay, by iteration I found this terminal velocity which we were looking for. Okay, great. So we found the first part. The second part says find the height or the minimum height of the tank which we can have this cooling from this hot one, which is 360 to 320. What is the minimum of this height which we can have to this phenomena happen? So we need to find that height. Okay, let's see how we are going to investigate that. So I'm going to start say, okay, I know what is the velocity of that ball or sphere. So we called it U infinity, and velocity is height divided by time. That's easy. So if I want to find height, I can multiply simply the velocity by time. Okay, now I need to know how long it takes for that sphere to cool down from 360 to 320. How long it takes. Okay, so now if I want to find the time for cooling an object, I'm going to remember, okay, last week we talked about this. It was about conduction, it was about lump analysis, and we had basically two solutions. let me go back and check this. So this is week 4, and we said we can have lump system and easily calculate time using this formula. To have lump analysis, you need to have BO number smaller than 0.1. And BO number formula for sphere is this. The characteristic length is L divided by 3, and this is the formula. If we couldn't have that BO number less than 0.1, now you need to use that differential equation, partial differential equation, and solve it. And we had 3 different equations for sphere. This one, if we had this tau or Fourier number bigger than 0.2, we could use this one term approximation, use this equation. If we want to find at the center, this equation, and we had some tables to do those things. So I'm going to go that procedure. So I want to know what's the time, so I need to check BO number. Let's write BO number formula. I just showed you. Let's check it again. Okay, for sphere, this is the BO number. It is going to be the average h times characteristic length, which is radius divided by 3 divided by k. Last week, I talked about this k. I told you BO number is about solids, don't make mistakes, so I'm writing S here to make sure we're not making mistake here. Okay, so let's plug the number and get the BO number to see if we have lump system or not. But it's not easy. We don't have h. The problem raised. We don't have h. To find h, we need to know Nusselt number. Okay, now I need to find a formula for a sphere to get Nusselt number. So this week's topic, it's going to be here. Okay, so let's see if I have formula for Nusselt number for the geometry of a sphere. So, okay, here, this is for cylinder. The second one is for a sphere, and this is the formula 2 plus some terms including Reynolds number, Prandtl number, and these viscosities. And this is the range for this formula. We must have Reynolds number in this range and Prandtl number in this range to be able to use this. Let me write this formula first. So Nusselt number formula for a sphere is going to be this: 2 plus 0.4 Reynolds number power half plus 0.06 Reynolds number power 2/3 times Prandtl number power 0.4, and that multiplied by mu at T infinity, mu at surface temperature power 1/4. Okay, so what are the parameters I need to know? Okay, I need to know Reynolds number, I need to know Prandtl number, and I also need to know this mu and mu infinity and mu s. So I need to find those. Okay, we decided to have velocity, or we use it u infinity as 2.1 meter per second. So using this, Reynolds number is going to be about 29,580 or something close to this. It depends on what nu you calculated, how you interpolated. Yeah, so if you find some number close to this, it's good. So we found Reynolds number. The next one I want to find is the Prandtl number. Prandtl number this equation doesn't say at what temperature. When it doesn't say, you need to use T infinity. So for T infinity, which was 280 Kelvin, or in centigrade is going to be, you just need to subtract 273, so it is going to be 7 degrees. And we need to find that properties. From where? From table A9. Okay, this table is available for you at the end of the textbook. I also give you the link for downloading this table, these tables, all those tables, which is free inside the reading section on the Learn JCU. Okay, let's go and check the table A9, which is about saturated water. So for 7 degree, so it is going to be between 5 and 10, I'm going to check the Prandtl number. So Prandtl number is here. Prandtl number is going to be between 9 and 11 because we have 7 degree. So I need to interpolate. If you do the interpolation, we are going to find Prandtl number of 10.26. Now I need to find mu at t infinity, so I can find mu at t infinity. Let's go back again there, and here mu is going to be here. So between 1.3 and 1.5 times 10 power of 3. So let's write it down. If you do interpolation, it's going to be 1.422 times 10 power minus 3 kilogram meter second. Okay, for the mu s, I need to find at surface temperature. So which surface temperature? The average surface temperature. So average of 360 and 320, which is going to be 340, or 67 degree. Again, from the same table, 67. So 67 here. Mu is going to be between here between 0.4 and 0.42. So if you interpolate this, you are going to have this 0.42 times 10 power minus 3 kilogram meter second. Okay, now we found all the parameters we needed. Now I'm going to plug all those numbers inside Reynolds number formula. If you plug all those numbers and do the calculation, the final Reynolds number is going to be 439 or something very close to this. Okay, we have Reynolds number. We can easily find H or average H. So average H is going to be Reynolds number times conductivity divided by radius. Okay, which conductivity? Is it for solid or fluid? You should know when we extracted Reynolds number formula or H formula, remember that green point I selected was inside the fluid, and it was so close to the surface of the solid, but it was inside the fluid, and I insisted to explain that several times because I didn't want you to make a mistake here and all the calculation would be wrong. So it is important to have a good understanding of how we extracted those formulas, so this selecting which one is going to be easy, because Reynolds number is talking about the fluid side, so that thermal conductivity is going to be for fluid. So we found Reynolds number 339. The thermal conductivity of fluid at T infinity, let's go and check it. It's 7 degree, so thermal conductivity is going to be 0.58, for example. 0.58 divided by diameter 0.02. So the convective coefficient is going to be 12,651 watt per meter square Kelvin, which is huge number. Okay, so we found H. Now we can calculate Buoy number. Let's find Buoy number. Buoy number is going to be H, which is 12,651 times radius divided by 3.01 divided by 3 divided by Ks, which is the thermal conductivity of the solid, which is stainless steel, and the question says it's 60. So if we do the calculation, it is going to be 0.703. Okay, this is bigger than 0.1. So the trouble raised, lumped analysis is not applicable. So we can't go easily use lump analysis formula. So we don't have this luxury here. Okay, so we know if we couldn't use lump system, you need to go for the second method, which is that complicated one. So let's go back and check those formulas. So I can show you here inside the week 4 summary page. So this is the formula for sphere. This is the original one, and I'm not going to use this one. I'm hoping to have tau bigger than 0.2, so I can use this first term, one term approximation formula, which is much easier. And if you go back to the formula, it says the center of the sphere has that temperature. So we are talking about center, so automatically I'm going to use this one, which talks about the center or the temperature of the center. So let's write down this formula and hope this tau is bigger than 0.2. If it's not, you can't use this one too. And you need to go back and use this one. So let's check and hope for the best. So let's write the formula for sphere at the center. So this is a sphere at the center, which is TO minus T infinity, TI minus T infinity, A1, this is a coefficient, e power negative lambda 1 square times tau, which is Fourier number. Okay, there's a point here. You need to be careful, and I ask you to write down this point, which is here. If you want to use these equations, the formula for Buoy number changes. You don't have that characteristic length r divided by 3 anymore. It is going to be r, just r. So I need to recalculate Buoy number. This time based on the equation they suggested. So H RO divided by Ks for the solid. So 12,651 times the radius is 0.01 divided by 60, which is going to be 2.108. Okay, this is the Buoy number for using the above formula. Okay, now I have this Buoy number. I need to find A1 and lambda 1. So let's go to our session 4 topic. So this is the formula, and to find A1 and lambda 1 I need to use this table for 2. The Buoy number is 2.1. So here, so for a sphere, lambda 1 is going to be around 2 point something, and for A1 it's going to be 1.4, and you need to again interpolate. So from table 4.2 you are going to get lambda 1, which is 2.06, and A1 1.478. Okay, we found those two, and let's plug inside the formula, this formula. So the left side for the temperature, it is going to be about half. For the right side, it is going to be 1.478 times e power negative 2.06 squared times tau. If you do the calculation, tau is going to be 0.264. Okay, lucky for us, this is larger than 0.2. So now we can say, okay, the method we did, all these calculations we did for the this finding the tau, it's correct, and one term approximation is applicable. Okay, if it wasn't bigger than 0.1, yeah, it would be very difficult for us to go back and use the original formula. Now let's write down the formula for tau, which is Fourier number or Fourier number. It's time times alpha divided by r square. Okay, so let's plug these numbers. I'm looking for the time, which is going to be tau. Let me write tau r square divided by alpha. So if you plug the numbers, again alpha is going to be for solid, be careful, it's going to be 0.15 second. Okay, so I found the time, so the height is going to be u infinity times time. So 2.1 times 0.15, which is going to be 0.313 meter. So the h, the height of the tank, must be bigger or equal 0.313 meters to have that temperature loss from 360 to 320 Kelvin. Okay, make sure I did my best to keep everything consistent and not to make mistake in calculation. I could have had some mistakes in the calculations, or when I rounded I made a mistake somewhere. So if you got a number close to this, it is okay. And yeah, so please try to solve this question before watching the solution, and you are going to see the points we mentioned during the lecture. They are very important, and you are going to see how they are going to be useful when you are dealing with this type of questions. Okay, let's see the whole question here. Okay, maybe not. Okay, thank you very much, and see you in the class.